Swayam Prabha. Digital India. Educated India.
Now we will take a circuit and its nodal analysis equations. Okay, then make changes to the circuit and see what changes occur in the nodal analysis equations. And in this lesson, I would strongly encourage you to pause the video after I make the change to the circuit, figure out what change happened to the nodal analysis equation setup by yourself, and then compare it to what I show you as the answer. Okay, this is a better way of learning than simply looking at the answers that I provide. Okay, I'll take the same circuit I've been using so far. This is I1, R11, R12,
R23,
R22, R33. Okay, and this of course is the reference node, and this is I3. By the way, by now it must be clear why I chose the subscripts the way I did. R11 is basically the resistance connected to node 1 and the reference node. R12 is between node 1 and 2, R13 is between nodes 2 and 3, and similarly R22 is from node 2 to ground, and R33 is from node 3 to ground, and so on. And I1 is the current source being pushed into node 1, and I3 is the current being pushed into node 3. Okay, now we also have the nodal equation set up for this, which is times V1, V2, V3 equals I1, 0, I3. Okay, now what we'll do is we'll make various changes to the circuit and see how this nodal analysis equation setup is affected. Okay, as I said earlier, please work out the effect of the changes yourselves and compare it to what I work out. Okay. So first what I'll do is, let me add another resistance here, RA. So please work out what happens to the nodal analysis setup because of this. In this case it's very obvious. The resistance RA is in parallel with resistance R11, so the conductances simply add up. Okay, and also if you remember what I said earlier, the diagonal elements consist of the total conductance connected to node 1. So simply GA will appear here. Okay, so this parallel combination tells you that wherever you had G11 earlier, now you should have G11 plus GA. Okay, and that's exactly what happens, and that's also consistent with the diagonal element being the sum of the total conductances connected to a particular node. Okay, now let me remove this. Now let's consider another change. Okay, so what I'll do is, let me get rid of this current source I3 and connect it in the opposite direction from what I had earlier. Okay, so please work out what is going to happen to the equations because of this. we have made changes to the independent source. So this will change only the right hand side of the equation. And again, the answer is pretty clear. This element, which was the total current being pushed into node 3, it was I3 and now it has become minus I3. That's all. And that's anyway pretty obvious because we simply reverse the direction of the current source. So this becomes minus I3. Okay. So now let's consider another change. Let me add a conductance between nodes 1 and 3. Okay. Let me add a conductance between nodes 1 and 3. So what does this change? Please work it out. Now when I add a conductance, obviously the total conductance at those nodes to which I add the conductance will change. In this case, nodes 1 and 3, that's where I added the conductance. So the total conductance at these nodes will change. So the diagonal elements corresponding to these nodes will change. Okay. So we have node 1 here. Before, the total conductance was G11 plus G12. Now it will also have G13. And this is for node 3. So again, earlier we had G23 plus G33. Now we will have G13 as well. So G13 plus G23 plus G33. Okay. Also, another thing that changes is the off diagonal element, because this conductance is connected between two nodes, neither of which is a reference node. Okay. So this element here, which was earlier 0, because no conductance was connected between nodes 1 and 3, now becomes minus G13. And similarly here, this becomes minus G13. The matrix is still symmetric because we still have a circuit consisting of only conductances and current sources. The matrix is still symmetric, and this is what happens to the nodal analysis setup. Okay. Now let's look at another change. Okay. So let me add a current source Ix between nodes 1 and 3 in this direction. Between nodes 1 and 3 in this direction. Okay. What changes do you expect from this? I have made changes to the independent sources connected to the circuit. So this will change the right hand side of the circuit. Now, what is this element? The first element of the source vector. It is the total independent current being pushed into node 1. Now it was originally I1. Now it will be I1 minus Ix because of the polarity of Ix which is connected. Okay. So instead of I1, I will have I1 minus Ix. Now node 2 has been untouched, so that will still be 0, and node 3, it will become I3 plus Ix. Because Ix, if you see, it is being pulled from node 1 and being pushed into node 3. Okay. So these are the changes that occur to the nodal analysis setup. Okay. And let me take one final example. Let me take one final example. What I'll do is, let me connect a current source like this, Ix between nodes 1 and 2 instead. So again, Ix is being pulled from node 1, so this becomes I1 minus Ix, and Ix is being pushed into node 2, so it becomes plus Ix, and I3 will remain as it is. Okay, so the source vector changes whenever you change the sources, which are current sources in the present case. Okay, so with this, hopefully the structure of the G matrix and the source vector, they are clear. Again, the solution of course involves matrix inversion. You can solve for it, but the idea of this nodal analysis is to have a systematic way of setting up equations for arbitrarily large circuits. So it is very important to understand the structure. Okay, because normally when you start off with circuit analysis, you look at the circuit and then maybe you identify something as the important loop or node to start off with, or maybe it's whatever is convenient for you. You start writing the equations in some ad hoc way, and finally when you have enough equations, you simultaneously solve them. But for large circuits, this won't work. Okay, we have a certain number of equations we have to set up, and we have to do it systematically. So this nodal analysis is one way of doing that. Okay.